Okay, what we're looking at now are a set of statistical methods called the non-parametric methods. Quite often you assume that the data comes from a distribution that's known except for a finite number of parameters. For instance, you might assume the data comes from a normal distribution. There's two parameters, the mean and the standard deviation of the distribution. Other methods don't make those assumptions. Those will be called non-parametric methods. The single sample tests. These are alternatives to the t-test and the z-test, which assume a normal population with two parameters, a mean and standard deviation. Both the z-test and the t-test are testing the value of the central location, the mean. We'll look at two non-parametric tests that do the same. They don't make the assumption of distribution. The Sine test. Carry out the Sine test. The test statistic is the number of observations that exceed mu naught. Another way of computing this is just to subtract mu naught from each observation and count the number of positive values there. The S observed is the observed value of S. It'll be 0 up to n. From that, you can compute the p-value of getting a value that extreme. You expect S to be around n over 2. If the value of mu naught is not the central value, S could be a large positive value or a large negative value. So we compute the p-value. Suppose we're doing a one-tail test. P-value is the probability of being less than the observed value of S. You double that for a two-tailed test. Then you could do that using the binomial distribution. You can compute it for large values of n using the normal approximation to the binomial distribution. Then if the p-value is small, less than 0.05 or 0.01, you reject H naught. That's the Sine test. If mu naught is the true median, S will be approximately n over 2. If the true median is greater than, less than mu naught, the number of positive numbers will be small, S will be small. If the true median is greater than mu naught, the number S should be large. Number of positive values should be large. Wilcoxon Sine rank test. This is a little bit more complicated. Again, it computes xi minus mu naught. Now, the Sine test just computes how many of those values are positive. What Wilcoxon Sine rank does, it ranks those differences from smallest in absolute value to largest in absolute value. Then W plus is the sum of the ranks associated with positive xi minus mu naught. W negative is the sum of the ranks for negative values. So W plus plus W negative, it'll be the sum of all of the ranks going from 1 to n. That'll be n times n plus 1 over 2. If the null hypothesis is true, W plus and W negative should be approximately the same, should be half of n times n plus 1 over 2. If H naught is not true, either W plus will be small or W negative will be small. So there's the case when the null hypothesis is true, true median is mu naught, then W plus and W negative should be approximately n times n plus 1 over 4. If the true median is less than mu naught, then most of the observations will be negative, so W negative will be large, W plus will be small. If it's the other way around, W plus will be small, W negative will be large. So to carry out Wilcoxon Sine rank test, you compute both W plus and W negative. That would be done by subtracting each observations from the hypothesized mean. Then those differences are ranked according to absolute value, and T is either W plus or W negative. Usually you pick the smaller of the two. Compute the p-value, probability of getting a value, that value smaller or not. There's tables for this. There's tables for this that can be used for when the sample size is small, less than 12, or and greater than 12. You can use what's called a normal approximation to the distribution of W plus and W negative. Once you computed the p-value, we include HA, reject H naught if p-value is small, less than 0.05 or 0.01. Two sample non-parametric tests. The test that we'll be looking at is called the Mann-Whitney test. It's for comparing the central locations of two populations. So it'd be similar, it'd be an alternative to the t-test and the z-test. You have a data coming from a population 1, x1 up to xn, a second set of data coming from population 2, y1 up to ym. Now, quite often the sample size is the same, but it's possible that they're different. If you assume that the data is coming from normal populations, then you can use the t-test and the z-test. The Mann-Whitney test is the non-parametric alternative. You compute, there's two statistics you can compute. You count the number of times an observation in sample 1 is below an observation in sample 2. An equivalent statistic is switching the samples around. Calculate the number of observations in sample 2 that are below observations in sample 1. Example. Here we're measuring bacteria counts for two types of cultures. We have 4 measures of culture 1. Those are the bacteria counts. There are the 4 measurements for culture 2. And our interest is whether one is smaller than the other, or possibly both ways, or just different. So you count the number of times an observation in sample 1 is below a number of observations in sample 2. There are the 8 observations combined. The superscript is really telling you what sample it is. So if I'm counting the number of times an observation in sample 1 is below an observation in sample 2, there's 3 observations below this 28.2. There's 3 observations below 29.2. There's 4 observations between 32 and 4 observations below 35. So the total number of times an observation in sample 1 is below an observation in sample 2 is the sum of those, 14. I can do the same thing for sample 2. There's no observations below 25. which is in sample 1, no observations below second observation in sample 1, no observations below third observation in sample 1. Then when I get here, there's 2 observations. So the total number of times an observation in sample 1 is below an observation in sample 2 is 2. No, that's sample 2 below observations in sample 1. Note that U1 plus mu2 in this example, 2 plus 14 add up to 16. That will just be m times n. That's every counting the number of ways you compare an observation in sample 1 with an observation in sample 2. This will always be true. For each pair, either one is below of one observation taken from sample 1, the other one from sample 2. Either one is below the other. In the first case, U1 will be increased by 1. In the second case, U2 will be increased by 1. And then there's a total of m times n such pairs. An alternative way of computing the Mann-Whitney statistic. Arrange the observations in the 2 samples combined in increasing order. Assign ranks from the smallest up to the largest. The sum of the ranks for sample 1, in this case, would be 1 plus 2 plus 3 plus 6. The sum of the ranks for sample 2 would be 4 plus 5 plus 7 plus 8. So U1 can be shown to be n times n plus n times n plus 1 over 2 minus W1. U2, the same formula, except you're using the second sample. If I add those 2 up, they add up to n plus m times n plus 1 over 2. And if you add the 2 u's up, they add up to n times m. The distribution of u has been tabled for various values of n and m. And these tables can be used to set up critical regions for test statistics. They can also be used to compute p-values. Example. This researcher's interested in measuring the brightness of paper determined by 2 different processes, made by 2 different processes. There's 9 observations for each type of paper made from process A and process B. These 9 observations are measuring the brightness. Now the question is there any difference between brightness, or is one bigger than the other? So take observations in process A and process B. Then you rank the observations in the 2 processes from 1 up to, I guess, the largest one would be 18. Sometimes observations are tied. 8.9 is tied with the other 8.9. 9.5 is tied with the other 9. 8.3 is tied with the other 9.5 tied with the other 9.5. So what you do in the case of tied observations, you average the 2 ranks. So 8, 9, 2 8.9s would have received a rank 13 and 14. You give them both an average of those 2 ranks. The 2 observations, 8.3 and 8.3, are tied, they would have been given ranks 9 and 10. You never need to. The sum of the ranks for A is 94. The sum of the ranks for B is 77. From that, we can compute the Mann-Whitney U statistics, UA and UB, n times n, plus n times n plus 1 over 2 minus WA for the A process. The B process is 49. Then from the table you can find that the chance that the Mann-Whitney's U statistic is less than or 18 is equal to 0.025. That's if we're using a two-tailed test. So the critical value for the U statistic would be 18 for both. They're both greater than that. So the null hypothesis is accepted. I could also find p-value for the most extreme one. Probability UA is less than 32, and double that. For large samples, we can use a normal approximation to the U statistics. If the sample size is large and the rule of thumb is greater than 10, these are outside the tabled values. The mean of each U statistic, if the null hypothesis is true, is n times m over 2. The standard deviation of each U statistic is square root n times m times n plus m plus 1 over 12. So then you can convert the U statistic into a standard normal statistic and reject H naught if Z is greater than the critical values in the standard normal distribution. The next test we're going to look at is an alternative to the one-way ANOVA test. Mann-Whitney U is used for testing the central locations of two populations. The Kruskal-Wallis test is for comparing the central locations of K populations. It's a non-parametric alternative to the one-way ANOVA F test, which assumes the data is coming from a normal distribution with possibly differing means and the same standard deviation. So the data is collected from K populations. The sample size for population I is Ni. So the data from population I is Xi1, Xi2 up to Xi. That data can be used to calculate the one-way ANOVA F test, which assumes data is normal. The Kruskal-Wallis test is very similar. You group all of the observations together and rank the observations from 1 to capital N. The smallest observation will be given rank 1. The largest observation will be given rank N. So the observations, the raw observations Xij, are replaced by their rank. Again, if there's tied observations, if a group of observations are equal, the ranks that are going to be assigned will be the average of those ranks. Then we compute the average rank for each sample. If there's no difference between the sample, the average rank should be approximately the same and approximately equal to the average rank for all the observations. For all the observations, the rank goes from 1 up to n. The average of that is n plus 1 over 2. If the K populations do not differ in central location, the average rank should all be approximately equal to and close to R bar. There's the Kruskal-Wallis. It's measuring how close the average rank for sample I is to the average rank of all of the statistics. The second formula is a computing formula. UI is the sum of the ranks for the ith sample. So that's probably easier to calculate. Second formula is the best computing formula for the Kruskal's statistic. First one will tell you that if the populations are all the same, Ri bar should all be close to R bar and K should be small. That's statistic. K, the sum of squares, it has a chi-square distribution. The degrees of freedom is equal to K minus 1. So you should reject H naught if K is large. K is greater than chi-squareds of alpha. Degrees of freedom is K minus 1. An example. In this example, we're measuring the enzyme level in 3 groups of patients who just received open heart surgery. The 3 groups differ in age. First group are individuals aged 30 to 45. Second, age 46 to 60. Third, age 61 plus. So what we're interested in is the enzyme level is there a difference between the enzyme levels between the 3 age groups? There's the data. We could use the one-way ANOVA F test to test whether the means were all different, but that assumes that the data is coming from normal distribution. That might not be the case. So there's the raw data. Here I'm performing the Kruskal-Wallis statistic. I rank the observations from smallest up to largest. The smallest is 70.2, the next smallest is 70.7, the next smallest is 81.1. So they're ranked from 1 to n is the total number of observations, which is equal to 50, 4, 6, and 5. There's the average ranks. There's the sum of the ranks for each sample. If the average ranks are all approximately the same, then the null hypothesis is true. There's no difference between the 3 age groups. So to find that out using the Kruskal-Wallis statistic, we'll use the computing formula. For there, I have to sum the total ranks for each sample squared divided by ni. So that's computed there. Then the Kruskal-Wallis statistic is that times 12 or n times n plus 1. N was equal to 15. Yep. That's 6.736. Looking up critical value from the chi-square distribution with 2 degrees of freedom, it's 5.99. Anything greater than 5.99, you should reject H naught. So we would conclude that there are significant differences in the enzyme levels between the 2 groups. We go back to the data, you can sort of see that the enzyme levels for the 46 to 68 year group, it's smaller. They have smaller ranks than the youngest age group and the oldest age group. At this point, we'll stop Next time for the next remaining lectures, I'll be just reviewing all of the material.